Hi everybody, I'm gonna present how we could visualize ONNX models using the Zetaine software and how we can use this visualization to improve the performance of our neural networks. So the Zetaine Viewer is used to open the AI black box, just like microscopes and telescopes and other like brain imaging techniques that open the new way to look at complex systems. With the Zetaine Viewer, we want to look at internal tensors of the network and internal structure of the networks and neural networks, and to get insights how to improve the models and how to improve the training of the models. And the free Zetaine Viewer can be used to visualize the architecture and tensors of the ONNX models. So you can easily load your ONNX model and see the structures and internal tensors. And to get the Zetaine Viewer, you can have a look at our GitHub page or our website page, and you can download it for Windows, Linux, or Mac. So in this presentation, I'm going to present some examples of how visualization helped us in a few projects. And I categorized the different aspects into 3 different groups of data, network architectures, and internal tensor inspection. And because of the limited time, I only focus on the segmentation problem. Just a few words on segmentation. So the goal in segmentation is to assign a label to each individual pixel. It's somehow like a classification, but for each pixel. And we have 2 different main segmentation categories. The first one is semantic segmentation, and in this, the second one is instance segmentation. So in semantic segmentation, we don't care about different objects from the same type, and we consider them as one class, as you can see in this example. But in the instance segmentation, we care about different instances of each category. So in this case, we have 6 labels or 6 classes. 5 for different people and 1 for the background. While in this semantic segmentation, we have only 2 labels, 1 for the people and 1 for the background. And to evaluate segmentation, there are different measures used. The first one is pixel accuracy, and the other more complicated indexes are Jaccard index and Dice index. And I don't go into the details, but as you can see, they can be some values between 0 and 1, where 0 means there is no overlap between the ground truth mask and the segmented mask, and 1 means a perfect and complete overlap between the ground truth mask and the segmented mask and the perfect segmentation. So let's go into the to see some examples of how visualization helped us improve our neural network architectures. As you all know, data is really important in deep learning. We need to make sure that we are feeding the correct and the good data to the network, because the network will learn what we have fed to him. So we need to make sure that the shape of the data is correct and the pre-processing and normalization is correct. And this is one example that we were trying to segment the lungs from the X-ray data, and we had very good results, so we were happy with the results, but just out of curiosity, we wanted to see what the model sees inside the network, and we noticed some strong activation at the top corner of the images in different layers. And we realized that the network is paying more attention to the tag compared to other parts, and this tag was used to make the data anonymous. And we realized that maybe by cleaning the data, we could improve the segmentation. So we tried to remove the tag by some image processing techniques, and we retrained the network. And after retraining, we could have a better results. Like we could improve the DICE score from 0.97 to 0.98. DICE score was already good, but we could improve it even by 1% more. And the histogram of the tensors were become more broad and wider, as you can see in this graph, compared to the old model where we have this strong activation. The other aspect in neural network, rather than the data, is the network architecture. When we are designing a network, we want to make sure that all layers are connected correctly, and we usually suffer from the copy-paste issues. When we copy the layer, when we are implementing a network, we copy the layer and then paste it, and we forget to change all the necessary inputs or outputs. And especially when we have a big network with lots of skip connections, and with different activation functions, with batch normalizations and concatenations, etc. It's usually difficult to make sure that the network architecture is as the shape as we wanted. So by visualization, we can see the network architecture easily in the Zetaine Viewer. In this example, you are seeing a unit, and you can easily see the U shape and all the connections between the encoder and decoder parts. And if we zoom more, this is another network, but we can see all the convolutional layers and the activation functions and the batch normalization and how they are connected to each other. And if we zoom more, we can see the tensors for each layers and all the statistical parameters of the tensors, and we can see visual weights. We can visualize weights and biases and all the tensors, inputs and outputs of all the layers in the network. And this is another example how we can use visualization to verify the network architecture design. We usually use a piece of paper and draw the architecture on that. But by using visualization in Zetaine Viewer, we can easily see the network architecture and make sure that the design is correct. And the last part, which is the most interesting part, is how visualization can improve the model performance when we look at more carefully at the internal tensors and the feature maps, filters, biases, and the histogram and parameter ranges, shapes, and number of tensors. So this is one example that we were trying to segment some COVID-19 lesions in the CT images of patients. And we didn't have good results, but we didn't know why. So when we visualized the network in the viewer, we realized that one branch of the network doesn't pass the signal, and all the neurons are dead. So we tried to add some batch normalization, and also we could use another activation function such as leaky relu. And after that, we could confirm that the signal is passing through this branch, and we could improve the results. This is another example when we were trying to segment the breast tumors in ultrasound data, and we didn't have good results for some patients, and we could have used error analysis, but like the usual way is to analyze the errors and try to find a way to improve the results. But what we did, we noticed that the histogram of the last layer is different when we have a good results compared to when we have a bad results or poor results. So at the top you can see some examples of good results, and you can see it's so sharp, but for poor results we have a more broad histogram. So based on this observation, we try to design an adaptive thresholding, and we could improve the DICE score in poor segmented images. by a good amount. So this is just one example. When this is the ground truth, this is before applying the adaptive thresholding, and the dice was 0.74, and this is after applying adaptive thresholding, and the dice is 0.82. So thank you very much, and if you're interested to use the viewer, you can have a look at our GitHub at Zetaine/viewer. And thank you very much.